Today I'm just going to be using the blackboard. I think I'm going to have too much material on the blackboard to have any time to demonstrate the Mathematica package today, so I'll probably do that tomorrow unless I find myself with extra time today. But I will give you the link, or was the link to the black hole perturbation toolkit already given to you all?
It's already in the
The toolkit is already in the email. Okay, so the packages you want to install from the black hole perturbation toolkit. Actually, did you give the link to the installation instructions?
So only to the main. I can send it to the.
Okay, I'll put it down here anyway. Otherwise, you just need to click through a few different links to get to it. Okay, and let me know if the writing is too small at the far end. Is that a yes? It's too small. Okay. Should I rewrite this? Let me.
I think this link I can send them to it.
Okay, but I just want to rewrite it anyway to get a sense of how big the writing needs to be for people to see it. Okay, how is this? Good? Okay. Okay, so this is where you install the packages. The particular packages you want to look at. Actually, how many of you have exact xtensor installed? Oh, quite a few. Okay, so those of you who have xtensor installed, you should install the package perturbation equations. This will not be the main thing I demonstrate, but because you need to install exact, and I don't want everyone to have to install exact, but do have a look at this one, and I will probably very quickly run through it tomorrow. Then the main one is the Tucholsky package. And to use that, actually separately, we also need the Kerr geodesics package. And you might as well also install the spin-weighted spheroidal harmonics package. Actually, I don't know if it's spin-weighted is actually in the title, but it's the spheroidal harmonics package. These will be the main two that you want to have, but anyone who has exact can install this as well, and we might want to make use of this last one as well. Okay, so today I'm going to be covering two things. One is kind of generic perturbation theory in GR. That'll be probably about half the lecture. So without specifying what the background space-time is, just kind of how you set up perturbation theory in GR in general. Then the second half of the lecture will be black hole perturbation theory in particular, where you're taking the background metric to be Schwarzschild or Kerr. So let's start with just generic perturbation theory in GR. So the idea here is we're going to consider some exact metric, G alpha beta, with a hat. So I'll put a hat on everything related to this exact space-time metric. And that's going to be equal to some background metric plus correction H alpha beta. where we're going to assume h alpha beta is small. Now, this does not mean I'm going to be working to linear order in h. Here, h is just being defined as the exact difference between the exact metric and the background metric. So this is going to have all orders in my small parameter encoded inside it. Now, what we want to do is formulate an Einstein equation, not for this, but for this, for the perturbation. So we're going to start with the exact Einstein field equations. Capital G hat alpha beta constructed from lowercase g hat equal to 8 pi t hat alpha beta. And now we want to expand this when h is small. So the first thing we're going to do is rewrite this in an exact formulation, so with no approximations, in terms of h. So the first thing I'm going to do is construct the difference between the Christoffel symbols in the exact metric and in the background metric. Because the capital G hat is constructed from the Riemann tensor, which is constructed from Christoffel symbols. So I'm going to define a tensor C alpha beta gamma, and use just 3 strokes like this to indicate a definition. So this is going to be the Christoffel symbol in the exact space-time minus the Christoffel symbol in the background space-time. Now, when you first learn differential geometry, or when you first learn GR, you learn that Christoffel symbols are not themselves tensors. They don't transform like tensors. But you might have learned that the difference between 2 Christoffel symbols is well defined as a tensor. So there's multiple ways to verify that. One is you just write down how this transforms. You write down how this transforms, and you just see that the non-tensorial part just cancels. Another more abstract way is to just note that if we take the covariant derivative in the exact space-time, so this is the covariant derivative that's compatible with g hat, if you take that and act on a vector, and then you subtract the covariant derivative with the metric compatible derivative on g, the background, so this is the background covariant derivative, the partial derivatives just trivially cancel. So if you write this in terms of this Christoffel symbol and this in terms of this Christoffel symbol, then you just get C alpha beta gamma V gamma. These are manifestly tensorial. Therefore, this is as well. So this is a well-defined tensor on the space-time manifold. With a very short calculation, we can show that this tensor is equal to 1/2 g hat alpha mu. So this is the inverse of the exact metric times 2 nabla beta h gamma mu minus nabla mu h beta gamma. So this is the covariant derivative compatible with the background metric acting on the perturbation. And this is an exact expression. Has anyone seen this before? Outside of special cases like flat spacetime or something? No? Okay. Okay, the way to derive this is to use, or the simplest way to derive it, one way is just brute force. You just plug in the expression for this, the expression for this, and just brute force it. A much easier way is to use Riemann normal coordinates at a point P where the Riemann normal coordinates are defined with respect to the background. So what that means is that the Christoffel symbol at the point P is equal to 0. You're all familiar with Riemann normal coordinates, right? Okay. Okay, so then if we write down C in Riemann normal coordinates at that point P, well then the second term just vanishes. So you just have the first term. And that is equal to 1/2 g hat alpha mu 2 times partial derivative acting on g hat minus partial derivative, again acting on g hat. So can anyone see how to get from here to here? What are the steps to get from this expression to this expression? Yeah, so there's 2 steps. One is that we use the fact that the Christoffel in the background is 0, meaning we can just replace this with the covariant derivative. Then there's one more step, which is to write this G as the background plus the perturbation. The covariant derivative with respect to the background is 0 when it acts on the metric, as that just leaves you with the covariant derivative acting on H, which is what we have here. Okay, next, we're building our way up to the Einstein tensor, or really the Riemann tensor, the Ricci tensor. As soon as you have the Ricci tensor, you have the Einstein tensor. So let's go to the Riemann tensor with one index up. And let's write that in terms of the Christoffel symbols. Everyone's familiar with the square bracket notation for antisymmetric combinations? Yes? Okay. So we've got partial derivative acting on the Christoffel, and then we've got products of Christoffels. Okay, and I want to express this in terms of that tensor C. So what do we think is the easiest way to do that? The easiest way is, again, to use Riemann normal coordinates in the background metric. But there's one subtlety. So these terms in Riemann normal coordinates are just trivially equal to the capital C. So at the point P in the Riemann normal coordinates. But why is this term a little bit trickier to deal with? Exactly. So I can't just say that this is the covariant derivative of C immediately, because we do not have the derivative of the Christoffel at P. This is not equal to 0. And so this you actually need to substitute that this is C, or sorry, it's gamma plus C. just need to keep this term here, where the partial derivative acts on the Christoffel symbol. But that term just gives us the background Riemann tensor. So that term, we have the background Riemann tensor, R, alpha, beta, gamma, delta. Then we have all these terms coming from capital C. And there, I can just swap out this partial derivative for a covariant derivative on the background. So we've got plus 2 covariant derivative alpha C. Can't even read my own writing. Now this is gamma. Alpha delta beta plus 2 C alpha mu gamma C mu delta beta. So this expression is exact. There's no approximations yet. So I'm just rewriting the exact Riemann tensor in terms of the quantity h and the background metric g. But now there's one subtlety here, which is that this isn't fully in terms of just the background and the perturbation, because I've got this g hat inverse here. And g hat inverse is infinitely nonlinear in h. I can't just write it as a simple linear expression in terms of h. So this depends on g alpha beta and its derivatives, and it depends on h alpha beta, and it depends on g hat inverse alpha beta. So we can't write the exact Einstein equation just in terms of g and h until we do an expansion of this inverse. So then we need to start introducing approximations, no longer doing things in an exact way. Did I get my indices right there? Alpha, mu, yes, okay. Okay, so I am going to write down the exact Ricci tensor. And I can get that just by contracting over alpha and gamma. So it's just an immediate consequence of that expression. So we've got r hat beta delta equal to the background r beta delta plus 2 nabla alpha C alpha delta beta plus 2 C alpha mu alpha C mu delta beta. So the Ricci tensor basically is the Einstein tensor up to a simple manipulation. And so this is basically the left-hand side of the Einstein equation. But now I need to expand everything for small h. So I'm going to give up on doing things in an exact way and start introducing approximations. So the only expansion that's needed is the expansion of the inverse metric, which is the inverse background metric, minus h with indices up. And note that I'm always going to use the background g. Say mu raises indices. I'm not going to raise indices with the exact spacetime inverse metric. I'm going to be using the background. So that's just a convention. Well, it's not really a convention. It's just what automatically happens in perturbation theory. So this is h with indices raised using the background space-time metric, plus quadratic terms, 1/2 h alpha gamma, h gamma beta, plus cubic terms, quartic terms, and so on forever. So now I'm just going to substitute this expansion into this expression to get an expression in powers of h. Now remember I said here h is a fully nonlinear definition. H is just the exact difference between g hat and g. So by expanding this in powers of h, I'm not going to end up with my final perturbative Einstein equations. I'll just have an expansion in nonlinearity. And then I'll have to do an additional expansion later to get my actual perturbative Einstein equations. Okay, so if we substitute this in here, then we get r hat alpha beta equal to r alpha beta plus a linear term that I'll call r1. I'll use square brackets to denote that this is constructed from the tensor h linearly if it has just one argument. So this is a linear operator acting on h plus a quadratic term. And there I'll give it 2 copies of h. So this is quadratic in h and the derivatives of h. Plus higher order things. But I'm never here going to talk about anything beyond second order. Now the linearized Ricci tensor, probably many of you have already seen. So I will write that one out explicitly as a reminder. Actually, let me grab some more board space. So this is the linearized Ricci tensor, which is given by -1/2 the curved space-time D'Alembert, which is g mu nu nabla mu nabla nu. How many of you have seen this before? Basically everyone. Okay, great. Okay, that D'Alembert acts on perturbation. Then we've got -1/2 nabla alpha, nabla beta, acting on the trace of the perturbation, plus nabla mu. So here I'm raising the index on the derivative, just using the inverse background metric. Nabla alpha h beta mu. But then it's going to be useful to rewrite that after interchanging these 2 derivatives. So I'm going to use the Ricci identity to re-express this with the derivatives reversed plus a Riemann term. Then I'm going to combine this D'Alembert with the Riemann term. So I have box h alpha beta plus 2 Riemann alpha mu beta nu h mu nu plus this thing, but with indices reversed on the covariant derivatives, and I'm going to merge this term here into this last term. And to do that, I define this thing called the trace reversed perturbation. So h bar alpha beta is equal to h alpha beta -1/2 g alpha beta g mu nu h mu nu. How many of you have seen this before? Basically everyone. Okay, great. Okay, so this is the linearized Ricci tensor. Very often you choose a gauge, and I'm going to get to gauge in a second. You choose a gauge in which this last term is identically 0. And then you just have this very nice wave operator, which is parabolic in most scenarios. I'm not going to write out the full second order Ricci tensor, because just writing it out would probably take a couple of minutes. It's not terribly long, but it's roughly 3 times as long as that. Now the structure of it, though, I will just schematically indicate. We have things that are covariant derivatives of h, contracted with covariant derivatives of h. And then we also have things that are h times a second covariant derivative of h. So every term has 2 copies of h. Some terms have 2 derivatives acting on h. Some terms have only 1. So every single term has exactly 2 copies of h and 2 derivatives. Okay, now, very often the way you learn perturbation theory at first is you're really just thinking of linear perturbation theory, and you just say, okay, h is small, and now I just set R1 equal to 0, or R1 equal to, I lost my stress energy, but equal to the stress energy tensor, or the trace reverse of the stress energy tensor. Now, if you do that, it's then impossible to satisfy the second order Einstein equation. Because this h, again, is the exact difference between g hat and g. So in fact, R1, even in vacuum, is not equal to 0 when it's constructed from that fully nonlinear h. So to get a sequence of Einstein equations, one in each order in perturbation theory, what we really want to be thinking of is a family, a 1-parameter family of spacetimes specified by some small quantity epsilon. So in emery's, epsilon is the mass ratio, but here I'm talking about just totally generic perturbation theory. So we have g hat alpha beta. It's a function of some parameter epsilon equal to the background. And then all the epsilon dependence is going to go into h. And now I'm going to do a Taylor series of h with respect to epsilon. So I'm going to write h alpha beta equal to epsilon h1 plus epsilon squared h2 plus things of order epsilon cubed. Now in self-force, you have to do a kind of complicated version of perturbation theory where these coefficients actually still depend on epsilon. It's not a strict Taylor series. But here, I'm going to assume that it is just a strict Taylor series for simplicity, meaning h1 and h2 are independent of epsilon. And similarly, I'm going to take the exact stress energy tensor. I'm going to write that as a background T plus epsilon T1 alpha beta plus epsilon squared T2 alpha beta plus order epsilon cubed. And then, again, I'm going to assume all these coefficients are independent of epsilon. So when I put this on the right-hand side of the Einstein equations, and when I substitute this into the left-hand side of the Einstein equations, so into these expressions, and ultimately into this expression, then I can organize things into powers of epsilon. And then we have a sequence of equations, because if the coefficients are independent of epsilon, and you have something like epsilon r1 alpha beta h1 equal to, or say, plus epsilon squared times something, plus etc., equal to 8 pi epsilon t1 alpha beta plus epsilon squared times something, etc. Then the coefficient of epsilon has to be equal on each side. The coefficient of epsilon squared has to be equal on each side. So then you get one equation for h1, one equation for h2, one equation for h3, etc. So I'm going to substitute this expansion of H into that Ricci tensor. So we have r hat alpha beta equal to the background r alpha beta plus epsilon r1 alpha beta acting on H1 plus epsilon squared r1 again, but now acting on H2 plus quadratic terms r2 acting on H1 plus order epsilon cubed. Okay, so now this is the left-hand side. I'm going to move this quadratic term to the right-hand side so it becomes a source. And then I get that g hat alpha beta equals 8 pi t hat alpha beta. This becomes a sequence of equations. First, the background equation. G alpha beta is 8 pi t alpha beta with no hats on anything. Then next, the first order equation, G1 alpha beta. So to define G1, G2, etc., I'm just taking the trace reverse of R. This is equal to 8 pi T1 alpha beta, and then G1 again, now constructed from H2, equal to 8 pi T2 minus, now moving the quadratic term to the right-hand side, minus G2 made from things quadratic in H1. And this keeps on going to all orders. So you always have the same linearized Einstein operator on the left-hand side, but then you're building up nonlinearity on the right-hand side. So if I went to third order, I'd have cubic things in H1, I'd have products between H1 and H2, and so on to all orders. Just keep getting more and more nonlinearity on the right-hand side. So those are the equations that we ultimately want to solve in most physical scenarios, as long as you're within GR and not doing modified gravity. More generically, in addition to the Einstein equation, you'd have some equations for whatever matter field is generating that T, that stress energy. And so then you'd have coupled equations between these perturbative Einstein equations and perturbative versions of whatever your matter equations of motion are. But here, let's ignore the matter, except what it introduces through the stress energy tensor. Okay, any questions before I move on to the next little bit? Yeah.
So what guarantees that the stress tensor can be, the exact stress tensor can be expanded in such a manner? I can see that it obviously gives the background Einstein equation.
Mm-hmm.
But is there any reason that guarantees that the exact stress tensor can be written in that form?
So if you do not have a stress energy tensor that's a smooth function of epsilon, or that at least admits an expansion like this, then you can't do perturbation theory in GR. So we are restricting our attention to cases where we can do perturbation theory in GR. So you could have things that are super highly singular at epsilon equals 0, and in some cases that would just prevent you from doing perturbation theory. But by virtue of the Einstein equations, it's actually T that comes first. You specify that you have some family of T's that is nice and smooth at epsilon equals 0. Then through the Einstein equations, that then implies for you that you're going to get the expansion of G, or of H, Okay, so this perturbative theory comes with its own gauge freedom. So we all know that the exact the exact theory of GR has a gauge freedom that is diffeomorphisms, coordinate transformations. Now, when you go to the perturbative theory, you get not only diffeomorphisms on the background, which are epsilon-independent transformations, you now, in addition, get transformations that involve epsilon, and we restrict ourselves to gauges where the coordinates are smooth at epsilon equals 0, basically. So we introduce a new coordinate x prime that's equal to the old coordinate minus epsilon xi alpha plus order epsilon squared. So I'll add the order epsilon squared after doing just the linear calculation. So this is an infinitesimal transformation or a near identity transformation. So it's new coordinates are old coordinates plus something of order epsilon, specified by a vector xi. So there's a little bit of trickery here. So these, are, of course, are not vectors. These are just 4 sets of functions. Xi actually really is a vector, but here I'm looking at its components, not the abstract vector itself. These are just the components of the vector. Okay, now what we want to do is look at how the metric changes under this small diffeomorphism. So we want to expand g hat in both coordinates and see what changes. So we've got g hat in the original unprimed coordinates. So let's say a function of the old coordinates and of epsilon. I'm going to then expand for small epsilon at fixed coordinate values. So we have g alpha beta, it's a function of the coordinates, plus epsilon h1, it's a function of the old coordinates, plus order epsilon squared. And then I'm going to do the same thing, but in the new coordinates. Got a g hat prime, which are the components in the new coordinate system. And I'm expanding in powers of epsilon at fixed new coordinate values. So I've got the same background metric, just evaluated at the new coordinate value. But then I've got an h prime that could differ and does differ from h. So there's a very, very simple way to derive how h prime relates to h, but actually let me keep this and erase this. But I'm not going to go through the simple way because it's a bit more abstract. It may be a bit harder to get if you haven't seen it before. So instead I'm going to just show you the naive way of doing it. The calculations are a little bit longer, but it's still quite simple. So I'm just going to do the coordinate transformation in the usual way. So we have g prime at x prime equal to the Jacobian partial x mu, partial x prime alpha, partial x nu, partial x prime beta, g hat mu nu of x and epsilon. So I want to express everything on the right-hand side in terms of the new coordinates x prime so that I can compare to this expansion down here where everything's a function of x prime. So that means my coordinates x I want to express as functions of x prime. And as well in this Jacobian, x is treated as a function of x prime. And so the function is, well, I just move this xi to the left-hand side. So x alpha is x prime alpha plus epsilon xi alpha plus order epsilon squared. So then, for example, this Jacobian is now just the partial derivative of this expression. So the first term gets you Kronecker delta. And then the second term gets you a derivative of the vector xi, a partial derivative. So partial alpha xi mu epsilon plus order epsilon squared. So you substitute this for the Jacobian, and you also do a Taylor expansion of g hat by substituting this into the argument there, and then Taylor expanding for small epsilon. So when you work through the calculation, what you get is that g hat alpha beta prime, evaluated at x prime and epsilon, is the old metric, just like I had over there, but now evaluated at x prime, plus epsilon. And so we get two kinds of terms here. One is the h1 that comes just from the fact that this g hat is equal to g plus epsilon h1. So we get this h1, but now in addition, we get terms coming from the vector xi, from the Jacobian and from the re-expansion of this g hat. So this is a function of x prime. And then all the terms involving xi I can write as a Lie derivative acting on the background metric evaluated at x prime. Everyone has learned Lie derivatives. Actually, okay, it looks like quite a few people have not learned Lie derivatives. How many people have not learned Lie derivatives? Okay, it looks like the vast majority of people have neither learned nor not learned Lie derivatives. Okay, so Lie derivatives are a covariant derivative that you can define without a metric. And so, you know, when you define the covariant derivative that's metric compatible, you're using parallel transport to move tensors from one point to another point. Lie derivative instead is using what's called the pullback. How many people have learned the pullback? Okay, significant number, but not everybody. So the pullback you can think of as just an abstract version of the tensor transformation you get from a coordinate transformation. So it's basically just multiplying by the Jacobian. That's the pullback. So the Lie derivative, you know, it considers 2 points nearby, and then it pulls a tensor here. It pulls that tensor back to here, and then compares that, so let's call that T prime. That's the Jacobian times T, and it compares that to the actual value of T at that point, takes the difference, takes the limit as this distance goes to 0, and that gets you the Lie derivative. Now, in terms of explicit expressions, the Lie derivative, not just of the metric, but of any tensor, so let me give it, I don't know, A alpha beta. You can have any number of components, but let's just pick 2 so we know how it acts on the metric. You can write this as xi gamma, partial gamma, A alpha beta, plus partial alpha, xi gamma, A gamma beta, plus partial beta, xi gamma, A alpha gamma. And so if it's acting on G, I just replace A with G here. So like I mentioned, you can introduce a Lie derivative without a metric. So if you write down its explicit expression, it doesn't involve covariant derivatives, it involves partial derivatives. But if you do introduce a metric and you use the Levi-Civita connection, so meaning the metric compatible covariant derivative, then anytime you have an expression like this for a Lie derivative, you can actually just replace all the partial derivatives with covariant derivatives. Both expressions are identically true. And the reason I'm mentioning that, because that means the expression, when it's acting on the metric, simplifies because this first term vanishes. Although whether it's not, okay, whether or not, which one is simpler in practice depends on whether you're doing a coordinate calculation or a covariant calculation. If you're doing a covariant calculation, it's more convenient to use the covariant derivative. If you're using a coordinate, if you're doing a coordinate calculation, it's way faster to just evaluate this than to evaluate the covariant derivatives. But here I'm going to keep everything covariant, so I'm going to replace the partial derivative with the covariant derivative. So this implies that the Lie derivative of G, the first term vanishes, and I just pick up these other two terms. But then in addition, I can bring the G through the derivative to lower the index on the C. So I get nabla alpha C beta plus nabla beta C alpha. And probably everyone has seen this form of a gauge transformation. If only in flat spacetime you would have seen this. Okay, so putting that all together, we now compare this expression to this expression for G hat prime. And that tells us that this thing in curly or in square brackets, this is H prime 1 alpha beta at the point X prime. So H1 under a gauge transformation gets shifted by this Lie derivative acting on the metric. Okay, now I'll also write down the second order generalization of this just to make a simple point. You won't need to do any calculations involving it. So at second order, really the key thing is that each new order, you get one new vector field. So I'm going to rename my vector field over there, C alpha 1, and then I'm going to have a second vector field, C alpha 2, and then if I want to write down the coordinate transformation in terms of these vectors, it's not just this simple linear shift we see here. We're now going to get things that are quadratic in C1. So we have X alpha minus epsilon C1 alpha minus epsilon squared C2 alpha minus a half C1 beta partial beta C1 alpha plus order epsilon cubed. So at this point, you realize that, okay, I shouldn't be thinking of gauge transformations as small coordinate transformations, because this is getting ugly, and this indicates to you that this is not really the right way to think about it. So the better way of thinking about it is is basically, what's the best way to explain this without pictures? Okay, I'm going to draw a picture of a stack of spacetimes, or of manifolds in general. Epsilon equals 0 is going to define my background, and then epsilon runs up from there. And say we want to calculate the metric or any other quantity at some value of epsilon. When we do this series expansions, we are expanding fields that are up here down along some curve to get to a point on the epsilon equals 0 spacetime. So just like we have a family of metrics, we can think of a family of manifolds with one metric on each manifold. And then what gauge transformation is doing is saying, okay, let's consider two different ways of expanding around epsilon equals 0. And then any field, including the coordinates themselves, so x, x1, x2, x3, x4, each of those is just a scalar field. And so each of those I can consider the expansion along either of these two lines. And then this expression is looking at the difference between these two expansions, both evaluated at this point down here, x. So don't worry too much if that seems too abstract. I'm just trying to give you some intuition for why I don't just have a simple shift by C2, I have this weird quadratic term. Now, we already wrote down that H1 prime is just equal to the old H1 plus Lie derivative with respect to C1 of G alpha beta. Now, the second order metric perturbation changes in a more complicated way, but still fairly simple. So we have the same thing again, but now constructed from C2. But now we also have a whole bunch of quadratic terms, or a couple of them. So we have 1/2 league C1, league C1, G alpha beta. And we have league C1 acting on H1. So these terms, you can already kind of see, this looks like a Taylor series, but rather than partial derivatives, you have covariant derivatives or Lie derivatives. And then this is just coming from the expansion of the metric. So again, the key thing here is that, yes, things get more and more complicated in each order, but the key thing is that each order, you introduce a new vector field. So you have freedom to specify your gauge order by order. So you can specify a gauge at first order, and then separately specify a different gauge at second order, and so on forever. Okay. Now what I wanted to mention, okay, so I still have the linearized Ricci tensor here. So I wanted to mention one common gauge choice, which is called the Lorentz gauge, where you set this term to 0. Yes?
I don't think I understand the second order transformation. So for first order, it's like sliding the manifold across Z alpha by epsilon amount. What does second order essentially mean?
So this is the way to think of it, this picture. Or this is the way I think is to think of it. So we have a stack of manifolds. We don't have a single manifold. We have a whole stack. Then we want to expand fields up here in terms of fields down here. When we do that, we need to choose some path that we are taking from here down to here. The gauge transformation is two different choices of path. So I'm doing an expansion down here or down here. Say this is the x and this is the x prime. So one way to define it is that this, I identify the value of the coordinate here with the value of the coordinate here, or with the value of the coordinate there. Two different points up here, but the same point down there. And then I just expand everything to whatever order I want, and then I look at the difference between those two expansions when evaluated down there.
And why are there no linear terms for Z2?
This is the linear term in C2.
Oh, no, for the coordinate.
This is the linear term in C2.
Okay.
Yeah. Okay, any other questions? Okay, not. Yeah, I'll just write down that Lorentz gauge condition more explicitly. So the Lorentz gauge is not one that gets used in black hole perturbation theory very often. It does get used in black hole perturbation theory when applied to self-force calculations, but much more often you'll see it in the mathematics literature, mathematical relativity literature. So the Lorentz gauge condition is that final term without the outermost derivative is identically 0. So that is, let me write it like this. The covariant divergence of h bar is 0. And so then the linearized Ricci tensor simplifies. And we only get that first term in brackets. So we have the box of h plus the Riemann tensor contracted with h. Now the reason I'm writing this down again is because I want to compare it to the linearized Einstein tensor, which looks almost identical to the linearized Ricci tensor if you're in the Lorentz gauge, and if the background metric is a vacuum metric. So the only thing that changes here is that I put a bar on top of h. So this is if the background Ricci is equal to 0. So the expressions are identical. It's just that one is in terms of h, one is in terms of h bar. And yeah, the reason that mathematical relativity people like this gauge is that this is now a nice hyperbolic operator. And so you can prove theorems about the Cauchy problem, well-posedness, and things like that. Okay, I'm now going to switch to black hole perturbation theory specifically. But any questions about this before I move? Yeah.
Just one question on this.
Yeah.
So if you add h prime 1 and h prime 2, is there any representation of it in terms of exponential of the Lie derivatives corresponding to psi1 and psi2?
Yeah. So, yes.
So you can compose them and get this subscript.
Yeah. So the easiest way to write this expansion here is an exponential. The easiest way to write this is an exponential. Then you write down the difference between the two exponentials, and that gets you exponentials in terms of xi. Yeah.
Okay. For a single vector field, I would have understood, but with psi1 and psi2, you just compose the exponential.
Yeah. So it's this is what's called a Knight diffeomorphism, where you do a sequence of transformations rather than a single transformation. Yeah. But intuitively, you can kind of think of xi1 plus xi2 as just being a vector. Let's say this was the unprimed, this was the primed, then, okay, I might be getting the direction wrong, but it's basically a vector pointing from here to here, but then mapped down to the bottom. So yeah, pictorially, just think of it as you draw the vector from one point to the other, and then you just drop it down to the bottom. That's basically what's happening. Yeah.
You're saying you're stacking up manifolds.
Yeah.
So I can think of them as like different values of epsilon.
Exactly. Yeah. Yeah.
So how does epsilon square, how to visualize
I would visualize it just like that. So now we're on a 5D manifold there, where epsilon is one of our dimensions, is one of our coordinates. So there's nothing linearized about that picture. It's pulling back from
some epsilon value
to epsilon equals 0. Yep.
so epsilon square would be
So the general pullback is the exponential. So we have, okay, spent a lot of time on this picture, but okay, let me reverse the direction of these arrows. Let's say this is a vector field x, tangent. This is probably way too small to see. This is a vector field x, tangent to this curve, and say a vector field y, tangent to this second curve. Then the pullback we can write as basically, let me specifically use g, basically like this. That's the pullback. And so I expand this, well, let me put epsilon there, epsilon. Expand this in powers of epsilon, looks just like an ordinary Taylor series. Do the same thing along this vector field y, looks like a Taylor series, so we get epsilon, epsilon squared, epsilon cubed forever. Then we look at the difference between the two, and that first order vector field is y alpha minus x alpha evaluated at epsilon equals 0. And similarly, you keep constructing the x's from this x and y. Does that make sense? Maybe? This sign is definitely right, which makes me think that this direction here is wrong. I think this should be going the other direction. So we take the vector along this curve, subtract the vector along this curve, and that gives me this vector down there at epsilon equals 0. Okay. Really, you only need to think about linear theory. Well, okay, no. To do self-force, you need to do second order, but don't worry about it too much. You can always just work with this formula and then at some point try to derive it yourself. You can just take it as a given and work with it. Okay, so I'm going to move on to black hole perturbation theory. So everything I've said so far has been for a generic background metric. And I want to specify that the background metric is Schwarzschild or Kerr. Now, of course, Schwarzschild is just an example of Kerr. But I'm going to treat the two different cases quite distinctly. So let's first look at Schwarzschild. So we all know and love the Schwarzschild metric, which I'm going to write like this, minus f dt squared plus f inverse dr squared plus r squared d omega squared, where f is 1 minus 2m over r. So once we're doing emeries, once we're doing self-force, this will be the background metric, and m of the big black hole. But we'll also consider a case where m here is the mass of the small black hole. Okay. Now, the key thing here is that this metric is static and spherically symmetric. And because of that, the Einstein equations, perturbative Einstein equations, are fully separable. Which means we can reduce the four-dimensional PDEs to one-dimensional PDEs. I can use this board now. So to explain how that works, I'm going to introduce what are called vector and tensor harmonics. And that's best done by splitting up my coordinates into two types of coordinates, which I'm going to use lowercase Latin letters and uppercase Latin letters for. So x, a, these are coordinates on the TR plane. So they don't have to be TR. They could be u and v. They could be u and r. They could be any coordinates constructed from t and r. But just for simplicity, we can take them to be t and r. And then theta A is theta and phi. Again, they don't have to be theta and phi. They can be any coordinates on the sphere of constant t and r. But for simplicity, you can think of them as just theta and phi. So these are the ordinary Schwarzschild coordinates in that case. So then I'm going to define the metric on the unit 2 sphere, which in ordinary theta phi coordinates is given by 1, 0, 0 sine squared theta. So then in terms of that metric, I can write my space-time background metric. Well, its t and r components are going to be just functions of r, unless you do a really crazy transformation. But because it's static, you would always want to avoid that, so that it would be just a function of r. Then the mixed components, so this is like t theta or t phi or r theta, those are always 0. And then the angular coordinates, or angular components, are r squared times the metric on the unit 2 sphere. I'm also going to introduce the Levi-Civita symbol, Levi-Civita tensor compatible with this metric. So that's 0 sine theta minus sine theta 0. So that's just the ordinary Levi-Civita tensor, but on this 2D polar manifold. And I'm going to introduce the covariant derivative that's compatible with omega. I'm going to write that as capital D. So capital D acting on omega gives me 0. So I'm just working with unit 2 sphere geometry here. Switch boards. Now I'm going to introduce vector and tensor spherical harmonics. So we're working with tensors. We're not working with scalars. So if we want to expand in spherical harmonics, we need to introduce new kinds of spherical harmonics. And really, what this means is vector and tensor spherical harmonics on the unit 2 sphere. And they split up into two types, what are called even parity and odd parity. So the simplest one is just the scalar harmonic, YLM. Then we have a vector harmonic, YALM, that is just the covariant derivative of the scalar harmonic. And then we're going to introduce a tensor harmonic, YAB, that's constructed from more derivatives. So dA, dB, acting on YLM, plus a half L times L plus 1, omega AB, YLM. How many people have seen these harmonics before? Okay, about half of you. Okay, so these kinds of harmonics have been used since the 60s, since the early 60s in Schwarzschild perturbation theory. There are slightly different definitions of them in the literature. This definition, okay, this one's always the same up to a factor. This one, sometimes people don't include the second term. The reason to include the second term here is that it makes it so that omega AB, YAB, is equal to 0. So this is trace-free with respect to the unit 2-sphere metric. And you can show that using just the eigenvalue equation for the YLMs. Actually, I'll write that down in a second. Now, the odd parity ones, we don't have any scalar odd parity harmonic. But we do have a vector odd parity harmonic. And so all the odd parity harmonics always involve this Levi-Civita tensor. So epsilon A C D C YLM. And then the tensor harmonic is minus epsilon A C D B D C YLM. So all of these harmonics satisfy their own eigenvalue equations, some with different combinations of covariant derivatives, and you get back the same function again. So the simplest eigenvalue equation is the one for just the scalar harmonic, which everyone should have seen many times, but maybe not in this notation, which is that dA YLM is equal to minus L times L plus 1 YLM. So when you first learn quantum mechanics or electromagnetism, you'll see the eigenvalue equation for the spherical harmonics, but you'll usually see the left-hand side written in a much more complicated way, but it just represents this, which is the Laplacian on the unit 2 sphere. Okay, so now we've built scalar, vector, and tensor harmonics, and we're now going to expand all of our quantities in terms of those harmonics. So, I'm going to expand Hn, the nth order perturbation, in harmonics. So if we first consider just the TR components, or the components on the TR plane, these are scalars with respect to the angles. So I'm going to expand them in scalar spherical harmonics. So L runs from 0 to infinity, M runs from minus L to L, and then I have H, A, B, N, L, M. And these things are only functions of the T and R coordinates. And then they're multiplied by the scalar spherical harmonic. function of the angles. Now if I consider the mixed components, so one TR component, one angular component, these are going to be expanded in terms of the vector harmonics. And then we start at L equals 1. Again, M runs from minus L to L. And I'm going to use some unusual notation that I find very convenient. So the even parity coefficient, I'm going to put a plus sign. So I'm always going to use pluses for even parity and minuses for odd parity. So I have HA plus NLM, it's a function of T and R, multiplying the even parity harmonic. And then I have HA minus multiplying the odd parity harmonic. Now if I look at the purely angular components, I'm going to have some tensor harmonics, but I'm actually going to have some scalar harmonics as well. The scalar harmonics come from the trace piece. So remember I said find this to be trace-free. That's why I've added this second term to make this trace-free, which means that I then need to add a piece that has a trace. So let me first write down that trace piece. So here, start from 0. M equals minus L to L. The trace piece is explicitly proportional to the metric on the unit 2 sphere. You can introduce an overall R here and an overall R squared here to make the coefficients dimensionless. That's just your choice. You can do it with or without. Here I'm not going to introduce the R and the R squared. And I'm going to write this coefficient of the trace piece, H circle, or H0, whichever one you prefer. And these are multiplied by scalar harmonics. Then I add the tensor pieces. So these start at L equals 2. So I've got H plus, with no indices, multiplying the even parity tensor harmonics. And I've got H minus, with no indices, multiplying the odd parity tensor harmonics. And so basically, any smooth tensor field on of at most rank 2 on spacetime can be expanded this way in these harmonics. So I'm going to expand the stress energy tensor in exactly the same way, and I'm going to expand the Einstein tensor in exactly the same way. So everything's going to get expanded in this same way. And then, once you've done that, the spherical harmonics just drop out of the picture. They separate the perturbative Einstein equations, and then you're left with equations just in terms of T and R. So the harmonics separate the equation. And this is because of the spherical symmetry. So we get a set of even parity equations. Right, it's GAB. And I'm going to stick to first order here for a second, but it goes straightforwardly to second order. So I'm going to say G1 LM. So I've expanded the TR components of capital G in scalar harmonics, just like I did the metric perturbation there. And then when I do that, this is going to be constructed from all the even parity coefficients. So when I write H even, I mean these guys, and these guys, and these guys, and this. So it's all the even parity coefficients. That's going to be equal to 8 pi t, 1 lm, ab, and the harmonics have just disappeared. This is just a PDE in T and R, or a set of PDEs in T and R. And then similarly, I get GA plus 1 lm, constructed from all the even parity pieces. And it's important here that this LM is the same as this LM. So there's no coupling between different L and M's. The LM component of the linearized Einstein tensor is built from that same LM for H1. 8 pi t, 1 LM, A plus, G plus, 1 LM, H even, 1 LM, equal to 8 pi t 1 lm plus, and so on. G circle, 1 lm, H even, 1 lm, equal to 8 pi t circle, 1 lm. So this is a set of 7 PDEs. Because I have, for example, the TT component, the TR component, the RR component. I have the T component and the R component. So that's 3, 4, 5, 6, 7. And these do not involve any of the odd parity coefficients. So in Schwarzschild, the even parity decouple from each other. And so then for the odd, we have GA minus 1 LM, constructed from H odd, 1 LM, equal to 8 pi T A minus, 1 LM, and same thing for G minus. Pi T minus 1 LM. So this is now 3 more equations, the T component, the R component, and this one. So we have 3 odd parity equations, 7 even parity equations. Each of these is PDE in T and R, and they're all coupled here. These are 7 coupled equations. They're all coupled here. These are 3 coupled equations, but they decouple from each other. You don't need to solve all 10 components simultaneously. Okay, now we're going to do one more thing to fully separate the equations. So let me put it here. So right now we still have 1 plus 1 dimensional PDEs. But because the spacetime is stationary, I mean, spacetime is static, but that you just need the stationarity. So we have one more step, which is to do a Fourier transform to get rid of the time dependence, to separate the time dependence. So for example, let's take any of those even parity coefficients, 1 LM. Let's say explicitly this is a function of T and R. I don't have to use these coordinates, but I need to use coordinates that are at least closely related to T to get this Fourier transform. This is going to be the Fourier transform of H N L M omega even. And the same thing applies for odd, just put odd and odd. It's now just a function of R, and then we've got the usual Fourier factor, e to the minus I omega t, and then integrate over all omega. And now, because of the stationarity of the background metric, there's no explicit functions of time in the Einstein equations. And so the only thing that happens is that when you have a t derivative, this just becomes minus I omega. It just hits this exponential. There's no other t dependence anywhere in the background metric or in the coefficients in the Einstein equation. All the t dependence is in the perturbations, and I've factored that out with a Fourier transform. So then I get 7 coupled ODEs in R for these coefficients. So for all the even parity coefficients, for each value of n, Lm, and omega. And I get 3 coupled ODEs for H odd n, L, and omega. So I've now fully separated the field equations. Now here I've jumped to n, whereas I was writing just H1 previously. So the reason I was writing H1 previously is that once I introduce quadratic terms, so if I have a quadratic source over here and I want to read off its Lm coefficient, that's actually going to depend on all of the first order modes. So it's not like you can solve for a single Lm mode at first order and from that get the same Lm mode at second order. No, in order to get a single Lm mode at second order, you need all the Lm modes at first order coupled together. But they do satisfy things like usual coupling of angular momentum in quantum field theory type identities. So conservation of m's, m1 plus m2 has to be equal to m. So if I want an m value for the second order field, then I look at 2 first order modes. They have to satisfy this relationship. And similarly, you have the triangle inequality. The difference between L1 and L2 is less than or equal to L, less than or equal to the sum of L1 and L2. So when you plug in terms in the second order source and the quadratic source, you're only going to get contributions from first order modes satisfying these identities. So from here, I mean, I have one first order mode with mode number L1M1, one first order mode with mode number L2M2. And similarly, I need omega 1 plus omega 2 equal to omega. Okay, I think I'm out of time. So that is perturbation theory in Schwarzschild. This is not how it's actually normally done, or most frequently done. Usually you make a gauge specification called the Reggie-Wheeler-Zerilli gauge, where you set this to 0, you set this to 0, you set this to 0. So you eliminate as much of the vector and tensor content as you can to reduce things down as much as possible just to scalars. And then you take a further step, and rather than working directly with the Einstein equations, you devise field equations for other scalar fields that are not coupled to each other. So rather than having 7, okay, say we start with these 7, we kill off this and this, so that's killing off three fields. That gets me down to 4 unknowns. But you can do better and get it down to actually just 1 unknown, 1 single scalar field, from which you can then construct those remaining 4 fields. Okay, I'm not going to go through that, but instead I'm going to introduce in the next lecture is the Tucholsky equation, which is a similar idea. You solve for scalar fields. From the scalar fields, you reconstruct the metric. Okay, so let's stop there. Or maybe we have a minute for questions if there are any. Yes? A second, yeah.
Yeah. So, I mean, if my field itself has a small parameter over vacuum, then T1 is identically zero. I have to keep terms to be non-zero. So in that case, does the first order perturbation theory actually work?
In that case, first order perturbation is fine, yeah.
T1 terms is zero because T2 is the order of epsilon squared, right? Because
So the way I'm writing things, you can have T1 and T2 and T3 be 0. you just have no matter in the system. You can then solve a vacuum equation for H1. Then you get quadratic terms that G2 from first order, then sources, second order modes, and you can just keep going to higher and higher order like that without ever introducing a stress energy tensor. Yeah.
And also for the angular HAV,
Yeah.
why does L
Here? So these identically vanish for L equals 0 and 1. So if you take the definitions that I wrote down for them and you plug in L equals 0 or 1, you get